great to be here. So what I want to do today is give you a little bit of a sense of what the Langlands program is. And I want to do this mainly by talking about a famous instance of the Langlands correspondence, which is the modularity of elliptic curves. But before I get there, there's two things I want to say. One is that the Langlands correspondence is sort of supposed to connect number theory to other areas of mathematics, such as algebraic geometry, representation theory, or harmonic analysis. And I guess it's really not just one correspondence, but really an entire web of conjectural correspondences. And the other thing is that it also kind of relates to some of the oldest and deepest questions in number theory. And so I want to start with a very basic question about whole numbers, which is you can ask, what are the last digits of perfect squares? And if you think about it, you see that you can have 1, 4, 9, 6, 0, and 5, but you never can have 2, 3, or 7, or 8 as the last digits of perfect squares in base 10. So that just never happens. And then you can ask more general question, what if you write your numbers in some other base? Can you predict what the last digits of perfect squares can be? So as it turns out, the question reduces to understanding the last digits of perfect squares in base given by a prime number. And so I want to think about this question. I'll write it down. Wow, this chalk is amazing. So thank you. We're going to take L to be a prime number that's at least 5. And let's take something from the example of base 10 that wasn't the last digit of a perfect square. Can 3 be the last digit of a perfect square in base L? And another way to formulate this question, that's a bit more sophisticated, is to say, is 3 a quadratic residue modulo L? This is an equivalent question. And that's what it means. It just means that the difference between 3 and a perfect square is a multiple of L. Modulo L means that we are ignoring multiples of L. Okay, and so this question can be answered using, or at least you can get a sense for the answer using Gauss's law of quadratic reciprocity. So this is given in the following way. So if I have two prime numbers that are odd, P and L, then what Gauss's law of quadratic reciprocity says is that there's a very close relationship between whether P can be a quadratic residue modulo L, or whether L can be a quadratic residue modulo P. So this is a symbol that's equal to +1 if P is a quadratic residue modulo L, and -1 otherwise. And the point is that these two symbols are related by saying that their product is -1 to the P -1 over 2 times Q -1. Oh, I don't have a Q. L -1 over 2. Okay. And so if I want to answer the question about 3, I'm going to take P to be equal to 3. And then you see from this relationship that, so I want to know whether 3 over L is +1 or -1. And so this depends on what L over 3 is. So it depends on L modulo 3, whether it's a quadratic residue or not. And it depends on what I get here. And this depends on whether L is 1 or 3 modulo 4. And so if P is 3, you see that the number, or like the sort of the answer, only depends on L modulo 3 times 4, so modulo 12. So it depends on where L lands on the 12-hour clock. And I guess the answer is really the number of solutions to the congruence x squared congruent to 3 modulo L. Right? The number of solutions is periodic with period 12. And this is really something surprising if you haven't thought about this before. So for example, I can look at some prime numbers, 13 or 37 or 1093. And so I can choose quite big prime numbers, and still the answer will only depend on where they land on the 12-hour clock. And so all of these land at 1. And so that means that the answer for all of them is the same. So the number of solutions to this congruence modulo L is the same. And well, we can ask for 13, you know, is 3 a quadratic residue modulo 13 or not? And well, 16, if you write it in base 13, has last digit 3. So the answer is yes. But then you can take some other ones. If L is 17 or 29 or 1637, well, then they all land at 5 on the 12-hour clock. And so again, the answer will be the same for all of them, and it will be the same as for 5. And well, here the answer is no, because 3 is not a quadratic residue modulo 5. And that's something that we already checked when we thought about base 10, for example. Okay. So what I want to do now is sort of start from this very old and beautiful result of Gauss that, you know, goes back more than 200 years, and look at more modern and more sophisticated versions of reciprocity laws. And so what do I mean by a reciprocity law? It's going to be pretty vague, but I want to think about it as some way to characterize the set of primes modulo which a certain polynomial splits into a product of linear factors, for example. So that's what happens here when you have solutions. Then x squared minus 3 can be broken up as a product of linear factors that correspond to those solutions, I guess. So I'm going to start out with how to characterize the set of primes L such that, let's say the first thing is the one that we did. So x squared minus 3 splits as a product. I'm going to ask for distinct linear factors. Right? And that's what quadratic reciprocity tells us. It's like you look on this 12-hour clock and you have the quadratic residues and the ones that aren't. And anyway, the other thing is, what if we did some harder polynomial? So instead of x squared minus 3, what if we looked at a cubic polynomial? And so, for example, I took x cubed minus x minus 1. And I want the same thing. Describe the prime numbers L such that if I look at this polynomial modulo L, this breaks up as a product of 3 distinct linear factors. And you can hope that maybe there's a reciprocity law, just like in this case, that would tell you, okay, it's periodic and this is the period, and so here's like the residues for which it works and the residues for which it doesn't. But it's not as simple as that. So it turns out you can't quite characterize it. But in this case, the best that we can do is write down a generating series for the number of solutions. number of solutions to the congruence x cubed minus x minus 1 congruent to 0 modulo f. And so, you know, if you have three distinct solutions, I guess you have to look in the generating series, and then you can identify the primes L that give you that. And so I claim, this is much harder to see. You cannot just deduce it by elementary methods, but I claim that the generating series in this case is given by G of Q times the product from 1 to infinity of 1 minus Q to the n, 1 minus Q to the 23n.
Maybe it's easier to see this one with black boards.
Sure, I can do that. I'm going to move on to the next one anyway soon, but. I mean, I'm not very tall, so we'll have to see how it works. But so I claim that if you just expand out this infinite product, you get a power series in Q, and the coefficients of this power series at prime numbers. So if I look at Q to the L, that coefficient is going to tell me about the number of solutions to this congruence. So I'm going to write this as a sum from 1 to infinity, Bn Q to the n. And then I claim that the reciprocity law in this case is that if L is prime and different from 23, then basically the number of solutions here, congruence, so the number of solutions, I don't know what to call it. Let's say ML. Then ML minus 1 is BL. And so the coefficient plus 1 will tell you the number of solutions. And then if you really want to know, say, what's the first prime for which this polynomial breaks up as a product of three distinct factors modulo L, then you have to expand this out until you get a prime L where the coefficient is 2, and sort of the first prime with BL equals 2 is 59. And so it's very hard to figure this out by hand. If you just have the polynomial and you try to see, you know, modulo what prime can I find three distinct solutions? But with the generating series, you can. Okay, so these are some, I gave you some examples here. In fact, these are not the kinds of things I want to look at. I want to look at even more complicated polynomials. So not in one variable, but really cubic polynomials in two variables. And so these are kind of some motivating examples that, I don't know, tell you can do some pretty fun things with these kinds of reciprocity laws. But I really want to look at reciprocity laws for certain cubic polynomials, more precisely for elliptic curves. And so what about y squared plus y equals x cubed minus x squared? So now I'm taking a cubic polynomial, but in two variables. And I'm asking still sort of how many solutions does y squared plus y congruent to x cubed minus x squared modulo L have? So how many pairs of xy mod L can you find that satisfy this congruence? And let's say that this number is NL. So, okay, so it's not going to be as nice as in the case of just a quadratic polynomial in one variable. But it turns out that it's very similar to this other case of a cubic polynomial in one variable, in the sense that you can again write down a generating series. So it turns out that we have a generating series so Q product from 1 to infinity, 1 minus Q to the n squared. Did I get it right? Yeah. 1 minus Q to the 11n squared. And I write this as the sum from 1 to infinity of an Q to the n. And then it turns out that the coefficients a sub L, where L ranges over prime numbers, know about this number of solutions to this congruence here. So the kind of the explicit reciprocity law in this case is that n sub L is equal to L minus AL. And this is for L prime. And I'll say L different from 11. I mean, in that case, you saw that 23 was a bit funny because it showed up here. And so I excluded it. And now I'm excluding 11, which shows up in this. Okay. And so these are all kind of examples from very elementary to more sophisticated examples of Langland's reciprocity. And so what's happening here is that really, so this cubic equation represents a rational elliptic curve. So you should think of it as, I mean, you should projectivize it, first of all, and then you get a smooth projective curve connected of genus 1 and with a preferred point, which is the point at infinity. And that's a rational elliptic curve. And then these generating series that I'm writing down in this variable Q, they're actually Fourier expansions of certain highly symmetric functions on the upper half plane that are called modular forms. And this reciprocity law is really saying that this elliptic curve is associated to somehow this modular form. So let me write this a bit more explicitly. Maybe I try to reverse them. Let's see. So y squared plus y equals x cubed minus x squared defines an elliptic curve. Okay, you have to projectivize. F of Q is the Fourier expansion of a modular form f of z, and here I take Q to be e to the 2 pi I z. So I claim there's some function on the upper half complex plane. I'll write a more precise definition in a bit, such that its Fourier series gives this expansion. And also, I guess this is also a modular form. It's just a modular form of a slightly different kind because it knows about polynomials in one variable rather than about these higher dimensional things. Okay. And the reciprocity law is an instance of the modularity of elliptic curves. The modularity of rational elliptic curves. The coefficients of my equation here are rational, even integral, I guess. Okay, so let me say a bit more precisely what's going on. I have the elliptic curve, and on the other side, I have a modular form. And this is the holomorphic function on the upper half complex plane. So I restrict to complex numbers with strictly positive imaginary parts. And maybe I don't give you the full definition, but I'll say it has symmetries under some arithmetic group, it's going to be some specific arithmetic subgroup of the group of 2 by 2 matrices with determinant 1 and with integer coefficients. So this SL2Z acts here via Möbius transformation. So Z goes to AZ plus B over CZ plus D. If I have a matrix A, B, C, D with integer coefficients and with determinant 1. And our modular form is just a function on here, holomorphic function, and with lots of symmetries, and I guess also with a growth condition towards infinity. And so the first thing is just to notice that these are objects that live in very different worlds. So this is an object of arithmetic algebraic geometry, because it's, I mean, you can think of it as a projective curve, so algebraic geometry, but the fact that the coefficients are integral also tells you there's arithmetic. And this is an object of really harmonic analysis. And they can be connected. So what does it mean for an elliptic curve to be modular or to be associated to a specific modular form? To make this precise, you have to consider the fact that both of these have associated to them some number theoretic objects, which are Galois representations. So E and F both get associated two-dimensional representations of the absolute Galois group of Q. So here, GL2QP, or some prime number P. And the modularity is the statement, in fact, that these Galois representations are isomorphic. Okay, and let's see, maybe, let me just add that in words. So one of the symmetries that F satisfies is that it's invariant under Z goes to Z plus 1. So that corresponds to taking the matrix 1, 1, 0, 1, and that will live inside this particular arithmetic group. And so that's the reason we can even talk about the Fourier expansion of this modular form, is that it does have this symmetry among the other symmetries that it has. Okay, so rho E, the Galois representation attached to an elliptic curve, is constructed from, well, the p-adic Tate module, or I can say kind of the compatible system of, I can look at the p to the n torsion points on the elliptic curve. These are going to have coordinates that are algebraic numbers. And so they're going to have an action of the absolute Galois group of Q. And they're going to be compatible as n varies. So when you put these together, you construct a two-dimensional Galois representation attached to this elliptic curve. And then rho F, well, this is much more involved. So this is very, like, you can basically picture it. It just uses the group structure on the elliptic curve. It turns out there are also Galois representations attached to modular forms, and those are constructed from the Étale cohomology of modular curves. So modular curves are certain curves, algebraic curves defined over the rational numbers, that have the property that if I look at the associated Riemann surface, so I look at it over the complex numbers, then it can be identified with a quotient of the upper half plane, and it's exactly the quotient under this group of symmetries gamma. So the point is that the modular form really in some sense lives on the quotient of H mod gamma. And in fact, this quotient has an algebraic structure and even a structure over the field of rational numbers. And so for this reason, you can also extract the Galois representation from there, kind of cut out precisely the piece corresponding to the modular form F. You have to use Heck operators. These are certain averaging operators that act on modular forms. And somehow our modular form is a really special one. It's an eigenform. It's a simultaneous eigenvector for these averaging operators. Okay, but sort of you can use these to cut out from the étale cohomology a piece that really knows about the modular form F. And then this isomorphism here is really what say Wiles and Taylor-Wiles and Roy, Conrad, Nyman, Taylor proved when they proved that all rational elliptic curves are modular. So maybe let me state this theorem from, I guess, almost 30 years now. Should I? Yeah. Or is there a better way to? I don't know. Did you? I see you have a sponge. How am I doing with time while I'm doing this?
30 minutes.
30 minutes. Okay. Right. Okay. I have. All right, so this is going to be my theorem A. Theorem A. And as I said, this is due to Wiles and Taylor-Wiles from 1995 for semi-stable elliptic curves, and then completed for all rational elliptic curves by Broy, Conrad, Diamond, and Taylor in 2001. Okay, and this says, so let E be a rational elliptic curve. Then E is modular. i.e., there exists a modular, and I'll just put this in parentheses because it's a little bit technical, but it's really important to make the theory work. So an eigenform, which means simultaneous eigenvector for these Heck operators, F such that rho E is isomorphic to rho F. Okay, and what I want to do is just explain how to get the really explicit reciprocity law from this isomorphism of two-dimensional representations of the absolute Galois group of Q. So what happens is that, say, if I take L, so in our example, I can take L to be any prime different from 11. 11 is also, you can see it on the side of the elliptic curve as being the one prime where the elliptic curve has bad reduction. Then I can look at the Galois representation attached to E, and I can evaluate it at a preferred conjugacy class that knows about L, the so-called Frobenius at L. I can make sense of this. And I can do the same for rho S. And okay, so the Frobel represents a conjugacy class. If I look at two isomorphic Galois representations, I evaluate them on the same element, I'm going to get conjugate matrices. And these matrices, if they're conjugate, they're going to have the same trace. And so the trace of this and the trace of this, you get an actual equality. And now, so this is constructed from the torsion points on the elliptic curve. It turns out that the trace kind of is essentially computing some kind of, I don't know, it's like you can compute it with a kind of counting point formula. So this is equal to L minus NL. So it's L minus the number of solutions to our cubic equation mod L. I mean, I should really write here L plus 1 minus NL minus 1, because I should keep track of the point at infinity. But in the end, this is what you get. So L plus 1 is kind of, L comes, well, H0 and H2. And then this comes from, well, this part comes from H1, the elliptic. And then there's a counting point formula for the number of points. And over here, this Galois representation attached to F has the property that this trace actually remembers the eigenvalue for the Hecke operator at L. And this happens to match with the L Fourier coefficient of the modular form. And so this is how you get this equality that seemed to come out of nowhere when I first wrote it. So that's why the Fourier coefficient at L really matches with this. It comes from this isomorphism of Galois representations. Okay, so I think now, maybe I can add something else before I take a short break. So consequences. Okay, so we know all rational elliptic curves are modular. And so what? Well, it turns out this is a really useful thing to know because it connects these two very different worlds. And so the first really famous consequence is Fermat's last theorem, of course. So it has applications to Diophantine equations. Right, so what happened was that one could cook up some elliptic curve from some potential solution to Fermat's equation, but show that there's no modular form that could possibly correspond to that. Okay, there's another consequence, namely, this establishes the Hasse-Weil conjecture for the elliptic curve E. So elliptic curves have attached to them certain analytic functions that are in some sense generalizations of the Riemann zeta function. So they're called L functions. So the L function of the elliptic curve is something one can define, but a priori it's just defined on part of the complex plane. And it was conjectured to have analytic continuation to the entire complex plane. But this was not known, and the way that you deduce this is from modularity, because modular forms also have L functions attached to them. And this relationship here tells you the L function of E matches the L function of the modular form F, and those are known to have analytic continuation to the entire complex plane. I guess it's a more reasonable to believe this because they're more analytic objects. It's more reasonable to think that you could sort of prove it directly within that world. Okay, and also modularity of elliptic curves has been an input. So this is needed in order to formulate the Burton-Swinnerton-Dyer conjecture for the elliptic curve E. But it's also been an input in many approaches to BSD. So input for BSD in ranks 0 and 1, as in the work of Gross-Daguier, and also the work of Polyvagin. So one starts with a modular elliptic curve, and that's useful. We're trying to understand something towards BSD. The reason why that's useful is, okay, so in fact, modularity can have more meanings. So it could mean this isomorphism of Galois representation, or you could say it's an equality of L functions, or you could say, in fact, there's a geometric relationship that says that you can realize the elliptic curve as a quotient of the Jacobian of the modular curve y gamma. So this more geometric meaning of modularity is what comes in here. But in our case, when we're looking at rational elliptic curves, these meanings are equivalent. Okay. So while I erase the next board, I don't know, if someone has any, yeah, if there are any questions about the case of rational elliptic curves, now would be a good time. So what I want to do for the rest of the talk is just tell you a little bit about, well, what's been done in the past 30 years. But really, I mean, the field developed enormously. And so I really want to just focus on this instance. So what's happened in terms of modularity of elliptic curves in the past 30 years. And I think even that, maybe I won't be able to quite cover everything. And so one thing that I said was that modularity of elliptic curves is an instance of the Langlands correspondence. Namely, I mean, I can tell you it's an instance of the correspondence for the group GL2 over the rational numbers. And well, there are many, many conjectural correspondences. And well, in order to formulate them, you have to make two choices. You have to choose a global field. So I really want to think about global Langlands. And so I want to choose a global field S, which could be, for example, a number field. So the rational numbers or some finite extension of the rational numbers. So the rational numbers, or maybe a real quadratic field. So extension of degree 2, but still totally real. Or an imaginary quadratic field, such as the field of Gaussian numbers. Or, I don't know, you could do other things like take a cyclotomic field by joining some p power root of unity for some prime p. It's bigger than 3. Anyway, there's lots of number fields around. Or you could take a function field, and I actually won't say very much about this, but you could take, for instance, the field of rational functions on some smooth projective curve defined over, say, the finite field Fp. And right, there is a version of the Langlands correspondence in the setting of function fields as well. And in many ways, it's, I don't know, this setting is much, there's much more geometry and much more flexibility, and so one can do more here. But really, I'm going to focus on the number field setting. And you need to choose something else, namely a connected reductive group. G over the global field F. And here, as examples, I'm going to take GLN, so group of n by n invertible matrices, or SLN, the group of n by n invertible matrices with determinant 1, or 2n by 2n symplectic matrices that preserve a symplectic form, or so on. I don't know, choose your favorite reductive group. And so for each of these, there's a conjectural correspondence. And I guess there's, sort of very varying progress on the Langlands correspondence in these very different settings. And what I want to do is look still at the group GL2, but increase the difficulty a bit here by working over a quadratic field. And then, well, we have two choices. We have the real quadratic and the imaginary quadratic case. And so in the real quadratic case, the following result was proved in 2013. So this is a theorem of Freitas, Lehong, and Sixek. So let F be a real quadratic field. Let E over F be an elliptic curve. Well, then the same thing is known in this case. Then E is modular. And well, what does this mean? In this case, it means that there exists, well, the analog of a modular form in this real quadratic case. So there exists a Hilbert modular form. Still F, such that the associated Galois representations are isomorphic. And so the point of the Hilbert modular form is that, so the previous case, I had a holomorphic function on the upper half plane and with symmetries under gamma, and we should really, I said, think of it as living on a quotient of the upper half plane by this arithmetic group. And so in this case, F lives on, you have to look at two copies of the upper half plane that correspond to the two real embeddings of your quadratic field, and then take a diagonal quotient by some arithmetic group. Gamma is going to be some finite index subgroup cut out by congruences from SL2 over the ring of integers in F. Right. And so one nice thing about this situation is that the space that F lives on still has the structure of an algebraic variety and even can be descended to some number field, so some finite extension of the rational numbers. So these are the so-called Hilbert modular surfaces. Okay, and so the good thing for that is that these have Galois representations attached to them, so you can make sense of what this object here means, and these Galois representations are not too hard to understand. But still, in this case, one needed a bunch of extra ideas. I guess that's why it took 20 years, say, from the first instance of this theorem until this theorem was proved. And maybe I won't write it down, but I'll just say that this uses, first of all, a refinement of the Taylor-Wells method for proving modularity that's due to Kissen. So he found a much more sort of geometric way to think about the Taylor-Wells method. And the role of deformation rings was clarified due to him. It also uses, well, somehow Wilson used a 3-5 switch in this case for proving theorem A. This uses a 3-5 switch and a 3-7 switch. So somehow more involved tricks. And I'll actually talk about this tomorrow in my second lecture. And also, I guess they also have a very kind of ingenious way of computing real quadratic points on a bunch of modular curves with small level. And these can have very high genera, and they use quite combination of techniques. So some Chaboti, some kind of sieve. I don't know a lot about those methods. But yeah, somehow computational techniques, they managed to understand real quadratic points on a lot of modular curves of small level. And that was important for proving this theorem. Okay, so, but I'll really say more about this in the second lecture tomorrow. And then last year, James Newton and I, let's see, how do I do it? Maybe I put this down and I this a little bit up. We were able to prove the modularity of certain elliptic curves over, well, of all elliptic curves over certain imaginary quadratic fields. So this was another 10 years after the result in the real quadratic case. So let F over Q be an imaginary quadratic field. And I have to put a technical condition on it. So such that the modular curve, there's a specific modular curve that is our obstruction to getting the most general theorem, x naught 15. So the modular curve corresponding to congruent subgroup gamma naught 15, such that this has genus 0 over F. Oh, sorry, not genus, rank. Sorry about this.
We were just wondering, does it have genus 0?
No, so this is an elliptic curve. This is genus 1. It has rank 0 over Q. And so standard conjecture, so I guess Goldfeld has a conjecture, and combined with BSD, predicts that about half of imaginary quadratic fields have this property, that this elliptic curve of rank 0 still has rank 0 over them. And about half of them have the property that the rank increases to 1. And then I guess 0% have higher rank. So I have this condition here. And then if I have a field that does satisfy this, and if I have an elliptic curve over it, and in this case, I have to assume it doesn't have complex multiplication, but the case of complex multiplication, it's easy anyway. So a non-CM elliptic curve, then E is modular. Okay, and I'm just gonna, I guess, end with some remarks about this theorem. Let's see. Maybe the first thing is that, so it's modular, and really what you're looking for in this case is a cohomology class in the cohomology of some arithmetic hyperbolic 3 manifold. So instead of a modular form or a Hilbert modular form, what you're looking for lives in the cohomology of something that doesn't have an algebraic structure. So kind of the modular form analog comes from the Betty cohomology. So I have hyperbolic 3 space quotiented out by some congruent subgroup, some arithmetic group that's finite index inside the SL2 over the ring of integers of F. But the point is this doesn't have an algebraic structure. So that's the first difference. And so the existence of Galois representations in this case, I guess, is, well, due to Taylor, but then to actually be able to work with them, one needs to use also Galois representations for torsion classes, and so one needs to use Schulze's famous theorem on the existence of Galois representations for torsion in the cohomology of these Bianchi or arithmetic hyperbolic three manifolds. So that's one thing. Maybe another thing is that the condition in the theorem, so on the rank of this elliptic curve, applies to Q adjoin I, Q adjoin square root -2, Q adjoin square root -3. And then I think you can go a little bit more and then you start seeing some fields over which the rank increases. But conjecturally, it's a little bit more than 50%. I think it's 53% or something. Okay. So of imaginary quadratic fields. Over the rest, so over the fields over which the rank increases, we can prove, like statistically, we can prove that 100% of elliptic curves are modular. But in practice, what that means is that there are two infinite families that we're missing. And those infinite families are basically the imaginary quadratic points of this and also of some other isogenous elliptic curve. And maybe the third thing I want to say is, well, okay, so we proved this theorem, but we built on work of a lot of people. So 3. And maybe I'll mention other instances of modularity and other work tomorrow, but I'll just say that this particular theorem relies on work of Caligari-Garrity. So they're the ones who figured out how one might prove some modularity lifting theorem, how one might generalize the Taylor-Wiles method to the setting of these non-algebraic spaces. So Caligari-Garrity, Schulze, because you need the Galois representations for torsion that he constructed. There's my joint work with Schulze that comes in as well in order to control those Galois representations. There's the 10-author paper that proved that these elliptic curves, maybe I'll write down all the 10 authors in the talk tomorrow. So this proved that elliptic curves of our CM fields are potentially modular. We don't really need that result, but we need a lot of the intermediate results that are, and basically the method that was introduced there. And then also work of Allen, Carre, and Thorne. And this is actually really crucial. So they prove some residual modularity results that you need in order to be able to spread modularity around with the Taylor-Wiles method. And I guess I'll sort of say more about how this all fits tomorrow. So in the first talk, I will just give a survey of the kind of vanishing results that were proved in this paper and then in later papers with a lot of recent contributions by people new to the field. And then in the second talk, I guess I'll give more details about how we actually prove theorem C. So I guess, going to finish early. So thanks very much for your attention.